Okay, today's lesson is about theoretical probability. We talked about probability yesterday. And theoretical probability is a ratio that's comparing the favorable outcomes to the possible outcomes. If every outcome is equally likely. So our formula in the little beige definition box says the number of favorable outcomes divided by possible will equal the theoretical probability. So favorable divided by possible will give us theoretical probability. So let's do example 1. We're going to find the theoretical probability of landing on 3 when we have a spinner like you see in example 1. So the first thing we need to know is how many possible landing spots are there on that spinner? 8. How many landing spots with a 3 on them are on that spinner?
1.
Only 1. So the probability is 1 over 8. We divide numerator divided by denominator, remember, which gives you a decimal, and then multiply by 100, and you get 12.5%. Okay? What's the probability of landing on an even number on that spinner? How many possible landing spots are there?
8.
Still 8 spots. How many even numbers are there? 4. So you've got a 4 out of 8 chance, which would be 50%, right? Okay? Because every section on the spinner is the same size, any experiment that you conduct with that spinner would be considered to be a fair experiment because you have the same chance based on experiment size. But if 2 events can't happen at the same time, they're called mutually exclusive. Okay, mutually exclusive events. And you know, I can't read good with or without my glasses right now. The way we write the probability of mutually exclusive events is we'll say, what's the probability of option A or option B? And the way we actually find that probability is we find the probability of option A and then we add it to the probability of option B. We add them together. Okay? So let's look at the next page. You see a probability rule at the top. If A and B are mutually exclusive events, then the probability of A or B equals the probability of A plus the probability of B. That's how we find it. So let's look at an example that involves 2 events that are mutually exclusive. In other words, they cannot happen at the same time. Okay? So use the spinner to determine the following theoretical probabilities. For part A, it says spinning a number less than 4. Okay? How many spots are there on that spinner? 10. This one has 10? Okay. 10 spots on the spinner. How many numbers on that spinner are less than 4? 3. So how many spots are there with a 1 on them? 1. How many spots with a 2? How many spots with a 3? 1. So you see how we do that? This is the probability of landing on 1. This is the probability of landing on 2. This is the probability of landing on 3. All of these are less than 4. Okay? But you can't land on all of them at the same time. You can land on one or the other, right? So you can land on 1 or 2 or 3. So see the word or right there? That tells us we're dealing with mutually exclusive events, and we need to make a fraction for each separate event and then add those together. So when we add these fractions together, we're going to get 3/10, and then you turn that to a percent, and you're going to get 33.3%. Or 30%, sorry. I'm thinking 1/3. 30%. So there's a 30% probability you can land on a number less than 4. Let's look at part B. It says, what's the probability of spinning an 8 or a 12? Can you spin an 8 and a 12 at the same time? No. It's one or the other, right? So what's the probability of spinning an 8? 1 out of 10. What's the probability of spinning a 12? 0, because there's not a 12 on the spinner, is there? So now we add those together. 1/10 plus 0 makes 1/10. And then when we turn that into a percent, we get 10%, right? Skill check A lets you practice with more theoretical probabilities. And look in the box, skill check A, where number 1 says probability red or yellow. That's going to be mutually exclusive events, right? Red or yellow. The word or tells me I'm talking about mutually exclusive events. Now, complementary events can't take place at the same time. Okay? In your book, sorry, not your box, you'll see a box. In your book, you'll see a box, a pink box that is labeled S, right? And it has a circle in it, and that circle is labeled A. So that's the probability of your event happening, is that circle. The box represents all the events. So every other event that would happen that's not your event is called the complement of A. And we do it like this, A with a little apostrophe behind it, okay? That's called the complement of A. You could put all this on a Venn diagram and see it as well, okay? So let's look at example 3. A bananagrams game has 144 letter tiles with the distribution listed. Find the probability that an E is not drawn as the first tile. Okay? So, how many tiles are in a bananagrams game? They said 144, right? 144 tiles in a bananagrams game. What's the probability that we do not draw an E? How many tiles have E on them? 18. So what's 144 minus 18?
126.
So 126 over 124 should represent the probability. Let's divide that. 126 divided by 144, multiply by 100, and we get 87.5% probability that we do not draw an E. So if we represented that like we did earlier, this circle would be drawing an E, and everything that was not an E would be the complement of that. There's 126 possibilities out here and only 18 in here. Okay? Does that kind of make sense? All right. Let's see. Skill check B on the next page lets you continue finding theoretical probability using the bananagrams tile distribution that we just used. We use probabilities to make predictions, to predict the results of something. So let's look at example 4. The contents of a bag of marbles is displayed in the table. Find the expected results if a marble is drawn and then replaced 50 times. It does say then replaced, right? Okay. So how many marbles are in the bag?
9.
No.
Or on the picture?
30.
Did you add all those up, Chloe?
No, ma'am, it shows the total number on there.
Where?
Where it says the word answer right underneath it says total number.
Oh, yeah. Okay, I see. Yeah. Yes, you can go do that real quick. Okay, Colton, tell me how many of each color we have. We have 9 blue. How many red?
8.
How many green?
6.
Yellow?
4.
And black.
3.
Okay, and you said there's 30 total. Okay, So we're going to find the probability that we draw a blue marble every time if we draw 50 times. So this is what we're going to do. The probability of blue, let's find out what that is. There's 9 blue out of 30, right? So we're going to say 9 over 30. If we reduce that to lowest terms, that'll reduce down to 3 over 10, okay? So our probability is 3 over 10, but we're going to draw 50 times. So we want to multiply the number of times that we're going to draw times the probability. And we get an answer of 15. So if we drew 50 times, there's a probability we would draw blue 15 out of the 50 times. Okay, does that make sense? Now, what's the probability that we draw a marble that's not green? First of all, we got to figure out how many marbles are not green out of the 30. There's 6 green, so 30 minus 6, 24, right? We reduce that to lowest terms and get what?
4 over
4 fifths. Now, how many times are we drawing? Again, we're drawing 50 times. So if our probability is 4 fifths and we draw 50 times, 40 of those times we're probably going to draw something that's not green. Okay? In 50 draws, we would expect to draw about 15 blue marbles and about 40 marbles that are not green. Now again, remember, there's 30 marbles in the bag. The only way this works is if after I draw a marble, I put the marble back. I can't keep it out. If you drew 50 times, eventually you wouldn't even have any marbles to draw from if you didn't replace the marble every time. Skill check C gives you some opportunities to practice that, and then let's look at an assignment. We're going to do 1 through 17 all. We're going to do (19 through 29) odd.
19 through what?
29 odd. And then let's do 37 and 38. You don't have to do the cumulative review today since you've only got half a day to finish your assignments.